Hello students, welcome back. In this video we're going to go through chapter 10, section 2, regression. So the key concept here is that we are presenting methods for finding the equation of the straight line that best fits the points in a scatter plot of paired sample data. That best fitting straight line is called the regression line. And the equation of it is the regression equation. We will discuss marginal change, influential points, and residual plots for analyzing correlation and regression results. Okay, so regression line is, so you are given a scatter plot. So you have a bunch of paired sample data. So then the regression line is going to be just the line of best fit, or the least squares line. So don't overthink this. You've been doing this since Algebra 1. It's any straight line, so this regression line is just going to be following the basic format of the slope-intercept form, which you know is y equals mx plus b, where m is the slope. Let me change that right. Yeah, sorry. M is the slope, x is the dependent variable, and b is the y-intercept. I'm going to change that right now, and you're going to have to wait for me. So I'm actually curious as to how many people watch these videos. So if you are watching this video, I want you to do this. Shoot me an email just saying, hello. Hello, Professor Cooperman. Hello, sir. And I'll give you like an extra credit point or something. I'm just curious to see how many of you actually watch these videos. Since there is definitely correlation between the views and the homework time that people spend versus how well people do on quizzes. So shoot me an email, I'll give you an extra credit point, or I can send you an email back saying great job, and you can show your mom the email that I sent you, whatever you want. Okay, so the regression equation is just going to be y hat equals b naught plus b1x. So that describes the regression line. So x is the variable, or the predictor variable, or the independent variable, and y hat is the response variable, or the dependent. So that's basically your output given your input x. So the objective here is we are going to, once we have our data points, we are going to find the equation. We are going to write a y equals mx plus b equation that best fits the data. So when we're dealing with sample statistics, we use lowercase b. If we are using population parameters, we use capital betas. Okay, just showing you the notation. The requirements, similar requirements as before, must be random samples. You must have generally a straight line scatter plot. And 3 is outliers have a strong effect, so we remove any outliers. And that's considered pretty important as well. So finding your slope and your y-intercept, you just have your equations over here. So b1, which is your slope, is just your r multiplied by the standard deviation of y divided by the standard deviation of x. Because standard deviation is the measure of variation, so it makes sense that that would kind of give you somewhere between all the data points. And then your y-intercept is given by this value over here, which is your mean of the y minus b1, which we calculate over here, times the mean of the x. Here is your complicated formulas to be able to do that. Again, I do not expect nor want you to do this by hand, but I want to show you where it comes from. Round the values to 3 significant digits. So let's now do an example. So use technology to find the regression equation. Okay, we are going to use the same example as last section. So we have those 23 data points showing you chocolate consumption versus Nobel Prizes. So requirement check, there are no outliers, it's simple random, it generally shows a straight line data, good, good, good. So we do the same methodology as we did in the previous section, where you have your variable 1 going down over here, we did the chocolate, variable 2 going down here, we did the Nobel Prizes, and then we followed the steps as I showed on the last slide. And then we got this, it's just the same output screen. And it tells you right up here, this is your regression equation. Y equals mx plus b. Here's your initial value, your equation right here with your slope. Okay, so the use of technology is recommended. And then all the technologies, no matter if you use StatCrunch or TI-84 or anything, it's going to give you the equation of generally negative 3.37 plus 2.49x, where y hat is the predicted Nobel Prize rate and x is the amount of chocolate consumption. So your book provides step-by-step instructions on page 498 if you don't like it the way I described it. So we should remember that the regression equation is just an estimate of the true regression equation of the population. So it's based on one set of sample data. The more sample data you have, or you have different sample data, it'll probably lead to a slightly different equation. It's just an estimate. So we will use this is just showing you doing it if you did it by hand. You can use the formulas to find it as well. Your B1 and your B0, plug it all together, and you get the same equation as well. But I don't want you to do the equation yourself. Please use technology and make your life easier. So now we will graph the equation. So we're going to graph the equation, the regression equation described by right here. Y hat equals negative 3.37 plus 2.49. And we get this. This is the Minitab display. You can also have the StatCrunch display as I showed you as well. So once we have our regression equation, we can now make predictions. Since we have a general line of best fit, we can figure out any x or y value once you just want to know what it is. So given an x value, what do I expect my y to be? Given a y value, what do I expect my x to be? You're just plugging in one of the variables and solving for the other. So it's a bad model if the regression equation does not appear to be useful for making predictions. A good model, you can use it. It's kind of self-explanatory. So 3, correlation. So we use the regression equation for predictions only if the linear correlation coefficient R indicates that there is a linear correlation. And then scope, we use the regression line for predictions only if the data do not go, is that right English? Only if the data does not go beyond the scope of the available sample data. So you wouldn't want to use this to extrapolate values beyond the limits. So basically you wouldn't want to figure out, okay, what if the chocolate consumption was 20? What would let's just project that further. You wouldn't want to do that. So you want to keep it within the limits of the sample data is what that's saying. So here is your strategy. I'm not going to read through that, but if you need help, go back and read that yourself. So let's go back to the example of making predictions. So let's do 2 scenarios. A, use the chocolate Nobel data to predict the Nobel rate for a country with the chocolate consumption of 10 kilograms per capita. They finally announced what the heck that actually means by chocolate. So if we're saying, okay, a country consumes 10 kilograms per capita of chocolate, using that equation, how many Nobel Prizes do I expect that country to have? And then B, predict the IQ score of an adult who is exactly 175 centimeters tall, given a mean IQ score is 100. So, a good model. So, scenario A, this scenario over here, that will be a good model. So the regression line fits the points well, and there is a linear correlation between the 2 variables. So because the regression equation is given as this, and that's a good model, we just plug in 10 for x, and then we spit out what our y hat is, and then we get a predicted Nobel Prize rate of 21.5 Nobel laureates per 10 million people. So now they tell us what that means. About time. Scenario B, bad model. So there's no correlation between height and IQ scores, so that would be a bad model. So we would say that the best predicted value for the IQ score of that person is going to be the mean, which is 100. Okay? So basically, have to have good models with good data to use the equation. Kind of self-explanatory, but it just shows you how to make a prediction if you have a good model. Okay, next idea is the marginal change. So the marginal change in a variable is the amount that it changes when the other variable changes by exactly 1 unit. So the slope, that's basically just the slope. So let's go look at the equation over here. So if this x is 1, you get your y value. If x is 2, you get your revised y2 value. So then how much is it going to go up? It's going to go up by 2.49 each time. So the slope of 2.49 tells us that if we increase x by 1 each time, the predicted value will increase by 2.49. And that makes sense. If I said to you, hey, if you want to go into this club, it's $10 cover charge and then $5 per drink. Okay, so if you go there and then you get no drinks, you still spend $10. So then x is 0. And you have the equation y equals 10 plus 5x. If you buy 1 drink, you spend $15. If you buy 2 drinks, it's $20. So each time x goes up by 1, y goes up by 5, because it's the 5 that's in front of the x. 5 is my slope. So the slope is going to tell you what your marginal change is. Outlier. So like I said, outliers are extremely significant when we're dealing with these. So let's just look at 2 things. So an influential point is a sample data, like a pair of data values that are strongly going to affect the graph. So here is the 23 data points graphed right here. In this graph right here, we added a 24th data pair with the coordinates 50, 0. And these are the lines that best fit. Look at how much that line changes. Pretty drastic. This right here, we have a correlation, a good correlation. We're happy. Just one data point way outside, one outlier, completely ruins everything. That jerk. So that's just showing you the significance of an influential point or an outlier. And the final concept is residual. Okay, what's residual? So for a pair of sample x and y values, the residual is the difference between the observed and the predicted. What do I mean by that? Okay, residual equals the observed y minus the predicted y. Observed being what the actual data says, the predicted being what the equation suggests the y might be. And that's given by this equation right here, which by itself, y equals y minus y hat. Well, I like it better with the words. This kind of seems repetitive. So, residual is, once again, the observed minus predicted. So let's look at it right here. This is a simple equation, or a simple example right here. So we have the sample point with coordinates 8, 4. And we are given this equation right here. So this is our regression equation. Y hat equals 1 plus x. So we can predict a y, any y value given a specific x value. So if we substitute x into the equation, we get a predicted value of y. But for x equals 8, the actual observed is 4. But I predicted that it would be 9. So I'm looking at where, x equals 8, we're over here. I predicted that this would be at around 9. But the actual value is 4. So that gap right here, that's the residual, and it's -5. Same for any of these. You plug in 12 into the equation right here, you get the y hat value should be around 13, but it's not. It's actually around 24. So the residual is the difference between the two of them, or 11, and so on. The least squares property is a straight line satisfies the least square property if the sum of the squares of the residuals is the smallest sum possible. So, what do I mean by that? A residual plot is a scattered plot of the xy values after each of the y coordinate values has been replaced with their residual value. So let's just look at what that means. So to construct a residual plot, draw a horizontal reference line through the residual value of 0. Then plot the paired values. So now you're not plotting x and then just the predicted or the actual y. You're plotting x comma residual value. So once you do that, there should not be any obvious patterns. It should actually look pretty random. And it should not look much wider or anything like that. I think I have a graph of it. So this is showing you an example. Yeah, I think slide 3 of this will show what it looks graphically. So we are going to get the residual values for it once we have our x values. And then this is what it looks like. So it's pretty random when you look at the x value when plotted against the residual. So this indicates a good model because it looks pretty random. This has a little pattern to it, so this would be not a good model. And this is not a good model because it gets wider as you get further and further out. So this is a good model because when you plot x versus the residual y, it is pretty random. You get, roughly some above, some below, some close, some further apart, but there's no obvious pattern. All right, that concludes chapter 10, section 2. Thank you.